Well, this is lesson number 6 in differential equations in Tier 6, and the title of this lesson is Math Models, which I'll call MMs, Chimera or Reality. Okay, now, you probably know that all modern models in science and engineering are basically math models, and they're trying to model some aspect of reality that we're trying to understand and to analyze. Now, as a future STEM professional, you really need to be aware of our situation. I feel it's my obligation as your teacher and mentor and friend to sort of tell you what it's all about. And a real question we have with any math model is, does it describe the reality of the situation we're interested in? Or is our math model simply what we might call a chimera? Now, if you've not heard this word before, a chimera is a thing that is hoped or wished for, but in fact is illusory or impossible to achieve. So that's the question. Well, now, any math model has got to be based on mathematics concepts that we understand, and we understand them well enough, and we also have adequate tools that we can analyze these concepts and draw conclusions from this model. Now, mathematicians have actually been inventing new mathematical concepts for really millennia, over thousands of years. And in fact, every new generation, particularly the modern world, invents new concepts. In fact, sometimes we forget and ignore concepts that came before us as we invent the new ones. As a matter of fact, infinitesimals were a very valuable concept that our ancestors used for a long, long time. And then for about 100 years, we abandoned them because we couldn't really figure how to fit them in to our modern math systems. And then later in the 1960s, we figured it out, and they're back in again. In any event, mathematicians and scientists and technologists have been developing new tools to solve these various math models, again, for thousands of years. So, for example, the Greeks invented the concept of geometry that we know today, known as Euclidean geometry. And the Euclideans used a compass and a straight edge to make various geometric constructions. Well, it turns out that these two tools were inadequate to perform certain geometric constructions that we'd like to do. For example, to trisect an angle, divide it into 3 equal parts. Well, a later Greek, after the Euclideans, Archimedes, came along, and he said, well, let's take the straight edge and put 2 marks on it. Now we have what you might call a ruler. And with this tool called a ruler, we can trisect angles. Archimedes showed us how to do it. That's just one ancient example. Now, numbers are very important in math, as we know, and they're very difficult to deal with unless you have a really, really good system of expressing them. And a long time ago, our ancestors invented the decimal number system, which turns out to be a wonderful system for dealing with numbers. And then we were able to create what we call algorithms or rules, methods or tools for doing addition and multiplication and division and square root extraction and so on. Now, if you don't appreciate these algorithms, which are taught, by the way, now very early in school, go back and take another number system you might have heard of called Roman numerals and try to do these things with the Roman numeral number system. Very difficult. And so, in fact, this decimal number system was a powerful, powerful concept and tool that let us really deal with numbers and arithmetic. Now, the tools that you learn to do arithmetic, the standard algorithms for multiplication and division and square root extraction, are still pretty difficult to work with certain numbers, a lot of numbers. Well, a couple hundred years ago, mathematicians invented something called logarithms. That's a new tool. And it made all these calculations much, much easier to do than they were before logarithms came along. In fact, there were certain arithmetic calculations that were really just virtually impossible before, from a practical viewpoint, that you can now do with logarithms. A wonderful invention. And then the slide rule was a mechanical tool based on logarithms. It really basically put a set of logarithm tables on a couple of pieces of wood that you slide together, and it made it even easier to use. Now, this is around the horse and buggy era. This was back in the 17 and 1800s. Trigonometry concepts were very important for dealing with triangles. And then, of course, the tools that you could build with them made other models possible. In fact, you could take a circular slide rule and put the trig tables on it. Now, probably the tool that was most significant in the history of mankind as far as modern science and technology goes was what is called the calculus. And this was invented in the late 1600s by Isaac Newton and some of his colleagues, and Leibniz on the continent and his colleagues. Newton and Leibniz are given the credit. And this was a fantastic tool. As a matter of fact, Newton was able then to create his theory of physics, his model of the world, and that was really the birth of what we call modern science and modern technology. And it was this tool of calculus and the concepts behind it that made all of this possible. Well, it turns out that you need to extend calculus into what are called differential equations, which is what you're studying in Tier 6. This is an extension of calculus, and this was highly developed in the 1700s by Euler and others. Now, the algorithms for both calculus and differential equations were essentially manual techniques for solving problems for the math models that you could set up with these differential equations. Now, as we've learned, of course, today, we have a modern tool which makes all of these old manual techniques essentially obsolete because the modern tool, like Wolfram Alpha, just does it automatically. Well, after calculus and differential equations came advanced multidimensional calculus and complex number theory, and then calculus over complex numbers. And all of this was developed conceptually back in the 17 and 1800s. Now, as I said earlier, all math models are essentially based on whatever existing math concepts are available at the time that the math model is being developed. So, for example, the only geometry that was known to our ancestors was Euclidean geometry. And Newtonian physics was based on Euclidean geometry. In fact, at that time, man, meaning all human beings, believed this was the only possible geometry. In fact, we were sort of in a box, mathematically speaking, as far as geometry was concerned. Newton's models that he developed were great for solving many problems and creating many new technologies. And as a matter of fact, a lot of modern industrial technology, particularly in the mechanical area, is based on Newtonian math models. However, much more sophisticated calculus and differential equations was necessary for the math models that were then used by Maxwell in the 1800s to define the models for electricity and magnetism, which is really then the father, the scientific father of all modern electronics and communication technologies. Newton didn't have the mathematical concepts and tools that Maxwell had. Those came later. Now, I realize this is sort of history, but I believe if you want to see where you're going to be going, you've got to see where you've come from. So, in the 1800s, man got out of Euclidean geometry box by inventing what are called non-Euclidean geometries. In fact, these geometries were developed by people like Riemann and Lobachevsky and others, and they were actually much more sophisticated than Euclid's geometry. Now, as a matter of fact, Einstein could not have invented his special relativity theories of 1905 without the tools used with Maxwell's equations. These were advanced differential equation tools and advanced calculus tools, and this is called special relativity. And when you finish Tier 6, you're probably going to be able then to study that and understand it without any trouble. In 1915, 10 years later, Einstein used a much more sophisticated mathematics based on sophisticated Riemannian differential geometry to develop what is called general relativity, and that includes gravity. Now, this is a much deeper and more difficult math model to understand than special relativity, and you'll need more advanced math training before you get to that, more than you're going to get in this high school level treatment of differential equations. Now, quantum theory, which led to quantum electrodynamics, was some of the most sophisticated math models then that we've developed in modern science. And in fact, our modern electronics and communication technologies are based mostly on that. Another example is, you're all familiar with GPS, Global Positioning System. Well, you couldn't have that with Newtonian physics. There's critical components of this model that depend on both Einstein's special and his general relativity theory. Time gets slower as speed goes up. That's special relativity. Time goes faster as the gravity becomes less. That's general relativity, and you have to make those two corrections to make GPS work. Couldn't have done it with Newtonian physics. So if you wonder about the importance of math models and how accurate they are, Newton's math models simply would not have permitted this technology to be developed. It took Einstein's models to do that. Well, what does all this mean to you as a future STEM professional or you as a STEM student? Any math model that's used today in STEM and sciences you studied is going to be based on current math concepts and tools. Now, it turns out that many of the current models we're still using are really based on the old manual tools. They wouldn't put a model together if they didn't think they could actually solve the problems that came with it. So they had to simplify their math models in order to accommodate the old manual tools. Whenever you develop a math model for some aspect of reality, you got to ask yourself, do I have the tools to solve the problems that this math model is going to create? Historically, we knew that certain math models were crude approximations of reality because we made simplifications so that we had the tools to solve them. A quick example, and you're going to see this in a later lesson, I'll give you an explicit demonstration of it, is a math model for a pendulum, a very simple idea. Well, a math model for the pendulum involves a sine of t, but that makes it difficult to solve in certain situations, so the sine of t was replaced by t. Remember, they're almost the same when t is small. So they thought, well, that model, even though we simplified it, will be just good enough. Well, it is good enough for certain things that you do. However, it turns out that this simplified model does not exhibit some behavior that we call chaos or chaotic behavior, and the sine of t model, the nonlinear model, does exhibit this behavior. And in fact, in the reality of it, experimentally, pendulums exhibit this chaotic behavior. So if you take the simplified model, you can't even predict that behavior. You don't even know it exists. Whereas with the nonlinear, non-simplified model, you can predict it and understand it. So I'm going to teach you more about that in a later lesson. Okay, this is going to be kind of a long lesson because I want you to really soak this in, and there won't be any exercises to do other than just maybe go back and reread this and absorb it. We're now in the year 2015 and 16 actually as I'm doing this. And we've reached a very interesting point in man's history. We've actually now got the most advanced technologies based on our current math models that we've ever had in the history of mankind. However, our current math models are also known to be inadequate in various ways. Here's the most striking example to my way of thinking. The two most successful math models we have today in physics are general relativity theory and quantum theory, both developed in the 20th century. These are both great models, and they're responsible for many of our current advanced technologies. But they contradict each other in situations where they overlap. There are fundamental, irreconcilable differences. We believe that general relativity model is a correct model for gravity. But recently we discovered something called dark matter, and we don't have any idea what it is. Maybe there's really something out there that's dark matter, or maybe general relativity is not an adequate model. Well, if that's not bad enough, even more recently, we've discovered something we call dark energy. That's a very different thing, and it's very enigmatic, and in fact, we have no idea what it is. So general relativity theory might be really wrong in some real fundamental ways, but we don't know. Can we create a better math model that explains it? We don't know. There's a lot of unknowns there. Einstein's math models of relativity dictate that nothing can travel faster than the speed of light. On the other hand, quantum theory implies there are instantaneous communications between two entangled entities separated by great distances. In fact, Einstein just really hated that. He called it spooky action at a distance. Well, the question is there something I'll call stuff that really does travel faster than the speed of light? And in fact, is there something that is non-physical in our universe that is superimposed on our physical universe? As a matter of fact, there's a man named Dr. William Tiller that believes this is true. He's come up with a model of it and some experimental evidence for it. In fact, I consider him possibly a modern Galileo. And he's not in the mainstream of physics. Most people aren't paying too much attention to him, but I think his ideas are very, very deep. In fact, I once read that Einstein believed that before we would really be able to resolve some of these problems, we would need a completely new mathematics to resolve these issues. Well, certainly the most advanced theoretical mathematics today is way beyond what Einstein ever dreamed of using. And in fact, we have new models such as string theory based on these very abstract mathematics. And of course, the question is, will a model like string theory supersede our old models? Now, I'm going to express for you my personal belief. And of course, you should take it with a grain of salt. It's just my ideas, what I think. I believe that we're going to have to develop some totally new mathematics in order to create math models that are closer approximations of reality than those we have today. As a matter of fact, I think what Stephen Wolfram indicates in his research, if I understand it at all, and summarize in his book, A New Kind of Science, would kind of indicate this. Now, I must say, in mathematics, in theoretical mathematics, the concept of infinity, or I should say infinity, since there's lots of different sides of infinity, it's thoroughly embedded in our modern theoretical math. It has been for a little over 100 years now. This happened in the very late 1800s and early 1900s. And in fact, it was very controversial when it happened, but it won out, and it's thoroughly embedded in all of our mathematics now. And quite frankly, I think it's led to much of the modern math that our current math models are based on. But it also leads to things that, for me at least, are very, very difficult to believe in terms of reality. And I won't get into that in any depth now, but if you study theoretical math, you'll begin to perhaps understand that. Well, this is just a high school level approach to differential equations based on learning to use the tool Wolfram Alpha to solve problems that STEM students are going to face in engineering and in science. We're going to continue our study of differential equations. Just remember that we're constructing models that will be to some degree approximations of reality. Just keep that thought in mind because you're going to have a long career ahead of you. And I want you to have a philosophical concept of what's involved. Never put too much faith in any given math model. There hasn't been one yet that hasn't proved to have certain inaccuracies or inabilities to predict certain things. In fact, you might say a man's got to know his math model's limitations. Any math model that you're ever going to use is an approximation of reality. It may be good enough for what you're doing, but then there's certain things it may not encapsulate. Don't be guilty of too much hubris. Newton was very humble, and he knew that he was still very ignorant, even though he was the greatest scientist of his day. Einstein was humble, and he knew he was still very ignorant. As a matter of fact, mankind is still quite ignorant. We all are. Now, there's a lot of things we know, so let's enjoy what we do know. Let's enjoy our technologies and our math theories. But as you go through your career, you're going to learn more and more. What we're going to do now for the rest of Tier 6 is learn more about differential equations. But what's really important here is we're going to be able to do things with differential equations thanks to the tool of Wolfram Alpha that you can't do manually. And this is going to open up all kinds of insights and windows of opportunity for you as you proceed forward in your STEM studies and your STEM career. So just keep these things in mind. I realize this has been sort of a philosophical and historical rant, if you will, but I think that I owe it to you. I wish that someone had told me all of these things when I was getting started. It would have been perhaps very useful to me as I went forward in my life. So it's Dr. Dell wishing you all the best, and I'll see you now in the next more down-to-earth lesson.